Hey everybody, I'm Christopher and I'm a master's student at Tokyo Institute of Technology, and I'm also working at a computational creativity company called Cosmo. And I'll be presenting our paper, SerumRNN, which I wrote with my supervisor, Hideki Koike. So the outline of this presentation is going to be some background about the problem, what we're trying to solve, and an overview of the system, an example of how it works, some details, some evaluation, and then kind of what we're trying to do next. So this is a picture of Serum. Serum is a synthesizer. So this is a tool that you can use to make music, specifically sounds. And these synthesizers are very complicated. They have many knobs that you can turn to change how the sound is sculpted. They also come with many presets. So these are sounds that were included with the synthesizer. Serum is currently one of the most popular and most used synthesizers in the audio sound design industry, which is also why we focused on it with our research. And this research in general comes from my frustration of not being able to learn how to use this thing properly. One reason for this is there's many tutorials online that are really good, lots of people giving great information, but they also learn through trial and error. So it's quite inefficient to learn how to program these synthesizers. And you always find yourself thinking, what is the correct way to do something and in which order should you apply certain effects? So this is why we're trying to tackle this problem of educating users on how to program a synthesizer. So some considerations that went into this were, most importantly, we wanted our research to apply to a synthesizer that is actually useful. So one that's used in industry, because some of the background research that exists is applied to toy synthesizers, which are really great for testing out ideas, but unfortunately, they're not very useful for the everyday user who wants to use kind of a useful and fully featured synthesizer. And we also wanted to prioritize kind of the education process. So we want the user's sense of ownership over their work to be preserved. What we want to avoid is a tool that you just throw at the sound and you get a bunch of numbers and you don't really know how to interpret those, or you feel like you didn't learn anything in the process. So this is why we took this approach of doing this kind of step-by-step. And the other thing is we want inference time to be reasonably short so that the user can experiment and try different configurations and use the system a lot so that they can learn more as well. So before we get into the system, we actually had to generate a bunch of training data. So what we did is we chose 5 effects of the Serum synthesizer. So these are effects that sculpt the sound after you have a bass sound. And we split the bass sounds that we use into 3 categories, starting with basic shapes, which are like a sine wave and a square wave. So they might sound like this. So that's a square wave and a sine wave. And those are very simple. And that's where we kind of start with. Then we have a more complicated starting point, which are advanced shapes. So these use multiple oscillators. So those are some examples of more complicated audio that we want to then sculpt with effects. And finally, we have modulating advanced shapes. So these also have a time component that changes. So all of these kind of bass sounds, these presets, have no effects yet applied to them. And then what we do is we apply up to 5 different effects to those sounds, which then sculpt the sound and change it. And a lot of the work with programming a synthesizer is actually adding the correct effects once you have your starting sound. So a lot of beginners, they know where to start with like the basic envelope of the sound and maybe the wavetable that they want to use. But then using the effects becomes an infinitely, you can go as far as you want with how many effects you apply, and it becomes a very complicated thing. So with the 5 effects, we cover quite a few different types of sound. We have a compressor, a multiband compressor to be specific, distortion, which makes the sound grittier, an equalizer, which boosts volume at different frequencies, a phaser, which adds phase to the sound, and reverb, which makes it sound like it's in a big room. And for each of these, we have different parameters. We have continuous and categorical. So continuous parameters are knobs that you turn from 0 to 1 and have a continuous change to the sound. And categorical parameters are essentially modes. So for example, distortion has a mode of different types of distortion, and there's 12 different modes that you can cycle through. So with these 5 effects and these multiple parameters, it becomes an infinitely exploding combination of different sounds that you can create. And then we have our 12 bass sounds split into 3 groups to see how well it works as we increase in complexity. And we also limit the values that we sample sometimes if there's only a certain usable range. So this is just to make sure we sample random sounds within a usable range. For example, distortion, if the drive is close to 0, it doesn't do anything. So there's no point in sampling it. And right now we sample uniformly. And then what we do is we do the cross product of different effects to create a very large data set of possible sounds. After this, the conceptual approach of our system was actually inspired by the image domain. There's a really cool paper by Microsoft called Exposure. And what this paper essentially does is, given some image that might be of low quality, so it's very dark or it's not retouched properly, it's a system that can automatically apply different image effects to the image to retouch it and then create a desirable image, which is of higher quality and more pleasing to the eye. And then you can think of, in this diagram, you see the different steps that are being taken to the image to make it better. You can think of each step is similar to what we do with audio. We start with some audio and then we add an effect to sculpt it closer to some desired audio. The techniques used in this paper are quite different from what we use, but the idea is very similar. So I recommend checking out this paper. It's super great. So a high-level system overview of SerumRNN is what we call it, is that we start with some desired audio input, and we convert our audio inputs into pictures, essentially by converting them into Mel spectrograms and also using the Kepstrel coefficients. And we also have some target audio, so some audio that the user wants to move towards, that they're trying to maybe recreate or that their favorite artist is using. And then what the system does, it runs it through a ensemble of models. So one kind of master model that picks which effect should happen next, and then a ensemble of smaller models that then program each effect depending on which one was chosen. And then what happens is we get a step. So the system chooses an effect and then takes a step in that direction and then gets closer to the desired audio. So it'll spit out, for example, the next effect is distortion, and you should adjust the drive to this amount. And then we get a new output audio, which we can feed back into the system and repeat over and over again. So I think before we go into how the details of the system work, it's useful to just hear an example. So here's an example from the advanced modulating shapes, so the most difficult type of sounds, which means that the system actually, this is probably the most difficult sound for the system to tackle. But let's say we start with this original audio, and we want to get some sort of sound like this. So you can see the target audio is much more processed. It's got way more distortion, an equalizer, and a phaser attached to it. So what the system does is it'll start with this, and then it'll say, okay, the next effect should be a phaser, which will get rid of the high end a little bit and phase the lower end. And then it'll spit out that we need to do distortion to get the grit in the high end. So now we've added all the grit up here. And then finally, it wants to equalize the sound to create a more balanced sound that matches what the target was. And now we have something that's almost indistinguishable from the target audio. So this is kind of how the system works, and this is the example for 3 effects. So this is the more detailed architecture of the system. So first, as input to the master model, we have a sequence of audio spectrograms or coefficients. And this sequence in the beginning is of length 1, because all we have is the initial audio that the user has started with, right? And then what we do is we concatenate that those pictures of the audio essentially with the spectrogram of the target audio to create a 2-channel image. So then what we do is we have a time-distributed CNN for the Kepstrel coefficients and for the spectrograms, which then get rid of they embed the features of the audio into a sequence of embedding vectors. So now we have two sequences of embedding vectors, which are concatenated together. And then what we do is we concatenate that with a one-hot vector, which is also a sequence that represents which effects have already been used. So this one-hot vector is of dimension 6. This is because we support 5 different effects, but the 6th dimension is reserved for when we're right in the beginning and we haven't used any effect at all yet. So then we concatenate all those 3 sequences together to get a sequence of embedding vectors. And then we run that through a bidirectional LSTM with a fully connected layer attached to it, which then outputs a probability distribution. So this tells us kind of the distribution of which effect we should apply next. So once we have our probability distribution, we can choose which effect needs to be applied to the sound to get closer to the target audio. And then what we do is we choose a smaller model from the 5 models that are available, 1 for each effect. And then we feed the smaller model the latest step in the sequence of inputs. So this step is then fed to the smaller model, which then outputs which parameters should be programmed on the Serum synthesizer to generate that sound. So in this case, it'll choose the effect model, it'll run through the latest step, and it'll output some parameters, which we then feed to Serum, which then generates a new sound. So the next step in the sequence. Finally, once we've generated this final sound, we can append it to the input and start again, because now we have a sequence of n+1. And this can be done up to a maximum of 5 times because we support 5 different effects, and the model is trained in such a way that it can only use an effect once at one at a time, so only once. This is the architecture of the individual effect models. So we used a very simple approach because we wanted to look at kind of the overall system and working together with these different models. So what this architecture does is it takes the input audio and the spectrogram and the Koppe coefficients, and it runs 2 CNNs over each one respectively, which then embed the inputs into features, which we then concatenate and then embed into an embedding layer. And then depending on the effect, this embedding layer is connected to different output layers. So for distortion, it would be a 12-dimensional categorical output, since we have the different modes of distortion. And then for the effects that have continuous outputs, we also have a dimensional continuous output that tells us how to turn the knobs for that effect. Next up, we have evaluation. So the question is, how do we evaluate the system? Obviously, we can listen to it with our ears and see how it's making the sound closer to the target audio. But we also want to be able to measure this mathematically. So we use 6 different metrics. 5 of them are quite standard and are used a lot in this area. And they're just the mean squared error and mean absolute error of the spectrograms of the resulting sound and the target sound. We also use log spectral distance, which is a common metric, and also the Euclidean distance of the Koppe coefficients. And we also use the Pearson correlation coefficient to look at the similarity of 2 sounds. Finally, we wanted to build a more custom metric that is a little bit more robust. And the way we do this is we actually measure the similarity between 2 sounds by taking multiple spectrograms using different fast Fourier transform window sizes, which then has different temporal resolutions. And we also take the logarithm of the spectrogram to get different spatial resolutions. And by doing this, we can assess the sound on various different dimensions, which allows us to get a more robust kind of evaluation of how similar the sound sounds. Also, we evaluate against several different baselines. So we want to evaluate the benefit of using an iterative and a system that that considers the order of effects. And we also want to compare to systems in relevant literature that typically approach this problem as a single one-shot programming problem. So the first baseline is just a ground truth system, which we call the oracle. So this one knows the order of effects that the target audio was made with, and then it'll apply the individual effect models in that correct order that the target was made with. we have then our system that you just saw. Then another baseline is the non-iterative system. So this is the same as the normal system, except that we figure out the order of effects all at once, and then we apply the individual effect models one at a time. The third one is non-iterative unordered. So in this one, we just choose which effects need to exist, but we don't consider the order of those effects. And we just apply them in the order of which has the highest probability of being in the sound. Finally, we have SerumRNN1S. This is our one-shot system. So this is looking at the target sound and the input sound, and will predict all the effects that need to be in the sound and apply all the individual effect models at the same time. So this is by far the fastest system. And then finally, we have a random system. This one just applies the effects randomly. And just for the record, inference time for our system is about 300 milliseconds per effect on a simple MacBook. And this means the one-shot system can do all 5 effects in 300 milliseconds, but the other systems at most for 5 effects would take about 1.5 seconds to complete. We also need to define a stopping condition for all of them except for the oracle, because sometimes there's less than 5 effects applied, and with no stopping condition, the systems would just apply effects over and over again. So until they've applied 5 effects in total. So the way we do this is we define a stopping condition that the system should stop when it's made a mistake, but we wanted to know how many mistakes we should tolerate, because the system may not improve the sound at each point. There might be a sweet spot where it makes a mistake and then non-monotomically improves the sound over multiple steps. So we graphed the system over how many mistakes are tolerated, and we found the sweet spot is tolerating 1 false step and then terminating at 2. So we evaluate the overall system against the 3 different preset groups and also against all the different metrics. And what we essentially saw is that the SerumRNN system performs really well, better than all the baselines, and also better than the oracle in a lot of cases, which was really great to see. And also when we listen to how the system performs, it's quite encouraging to hear how similar it is to the target audios. When we also zoom into the kind of more specific results, we noticed that the error at each step is the greatest in the first step and then gets lower as we apply more steps. And this error has been normalized for how many steps were in the target audio to begin with. So what this means is that the system is actually prioritizing which effects need to be applied first to eliminate the most error, and then kind of prioritizes in that order. The counterpoint to this is the random system, which does just random effects. And as we see, the error is about the same at every step. So that means the order of effects is obviously important and is something that the system is learning. So the next steps for this system are mostly we want to expand the training data set to more than 12 presets so that we can ideally support all the presets that come with the Serum synthesizer. It's about 100 or so. And we want to sample our training data more efficiently, because uniformly sampling is quite inefficient and there's a lot of sounds that are repetitive or don't sound great. Also, looking at audio similarity with just math is not ideal. So we'd like to do a user study for evaluating audio similarity. And most importantly, we also want to package the system into an Ableton for Max for Live tool so that it's easy to use in a digital audio workstation and other people can take advantage of it. So this is similar to Magenta's tools that the Google Magenta team built a lot of their tools into these Ableton Max for Live. So we'd like to do something similar. And ultimately, we focused on timbre with this research, but we'd also like to explore learning kind of time-based controls like envelope and modulation. That's something we'd like to look into in the future. So I really encourage you to check out the website. There's examples generated randomly for all the different presets, and we kind of chose them just based on variety of sounds. So it's a relatively representative view of what the system can do. And it's kind of fun to see how it changes the effects and applies them one by one. And you can check out the full paper there too. And that's it. Thanks so much.
Fantastic. Thank you, Christopher. We have time for some questions. If anyone has a question, again, you can just post your question in the chat or if we want, you can unmute your mic and ask the question.
I'd like to make a comment, or it's sort of a question, I guess, but have you considered exploring, I mean, first of all, this seems like this could be a huge game changer for people being able to be creatively empowered to create sounds that they sort of know what they're after, but have no idea how to reach that. So I think it would be very interesting for you to associate tags that identify characteristics of resulting sounds, and then someone could, for example, say, okay, I'm after a sound that is gritty and, you know, distorted, or whatever, you know, various descriptive terms that have been associated with identifiable characteristics, that your system could then say, okay, to get from here to there, this is what I need to do, which would essentially mean that a creator could just say, here's the type of sound I'm after, and your system would just be like, okay, here you go.
Yeah, that's a really great comment. I've actually, some of my other research is related to capturing, you know, what kind of sound defines a certain artist, which is similar to kind of what type of sound exists with different genres. And yeah, like one thing that we were actually looking at is how do we sample our presets and our effects more effectively, such that, for example, we could use maybe discriminative methods that look at, you know, which sounds are the most different, and then within maybe a latent space or something, be able to kind of assign tags or something. So it's a really great thought. And this is just the tip of the iceberg, I think, for this kind of research. And we're really excited to kind of continue looking into this.
Great. Really cool stuff.
Thank you.